Yeah, so this is my technical um, analysis of my algorithm, the technical code, the logic itself. So yeah, I have the bubble sort, the insertion sort, the quick sort. I bring all the sorting algorithm together, then I run it in the main. So this is my bubble sort syntax, and what I was able to do is I was able to get the logic, get the timing, the start time, and the end time. Then that's how I was able to get the duration. I get the swaps and the comparison and the duration in nanoseconds, even for all the insertion cells and create cell, everything all together. I get their sap, their comparisons, I get their duration in nanoseconds, but I later convert the nanoseconds to milliseconds. And the reason why I convert it to milliseconds is when I'm dealing with graphing with the chart, it can be more presentable, it can be more explainable. So that's why I was able to convert it. So this is my bubble sort class, and this is the code. And we have also for the insertion sort. This is the code for the insertion sort, the logic, and this is where it's printing out the results. This is where the conversions happens. And we have my quick sort, and this is the method that runs it, and it's called this method at the top. First calls the partition, then it calls the recursive one. So, and everything is being executed here, and we generate the results here. And then we have the sorting testing, and this is where I test my result. Upon depending on the kind of size I want to use. So if I go to my main here, I have where my code runs. We have the sizes. The sizes either the small, medium, or the large data set. So I make the small 1000, the medium 5000, and the large 10,000. And this is where I'm calling on the sorting class, which is here, to help me to sort my data. So I'm passing the size of this, I'm passing it inside the sorting test. So it comes here, then it runs this, it generates the random data of the first thing that we have there is we have 1000, then it generates it comes here, load 1000, generates 1000 random data, and also it sorts the data from here. Then it then runs all the tests for either the bubble sort, this is the random set logic results. It's either run the bubble sort, the insertion sort, or the quick sort, and also it repeats itself like that. And when it runs that one, it runs the second value also, which is the medium 5000, and it's run the 10,000. And when it's running, it also runs we have to run it one by one. So we also run this is the code for the random data sets, and this is also the code for the sorted data, the random sorted data. So if I come to my main, I first of all run the random data set. Yeah, so it's run the already sorted data, which is the base case, and this is insertion, the time execution, bubble sort, time execution, and this runs for the medium size. It runs for the small size, for the medium size, and also for the large set. And also I can also run so that's one. This one should run the already sorted data first, and I can uncomment this one, and it should be run the random data set, the one that is not sorted. So if I come here to my main and I can run it, and this is the result for the random data set. For the largest, we have the time, the bubble, and the quick sort. We have the this is the medium size, 5,000. For the bubble sort, we have the quick sort. The same thing with for the largest number too. We have the insertion sort, the time, bubble, and the quick sort. Yeah, so from my code, and this is the random data set that is being generated. The random data set that is not sorted, this is the random one, and it's unsorted. And this is the time taken for the algorithm to run for 1,000, 5,000, 10,000, and these are the outputs for the random data set. Now, plotting the graph of the inputs and the time taken, we plot it against each other. We have the time taken, the vertical axis, and the input size, and the horizontal axis. And this is the chart. And this is the graph. This is the visualization of the chart. And let's explain, and we can say that the blue line is the insertion sort for the random data set, the red is the bubble sort, and we have the quick sort is the yellow, which is lined and flat. And now this, as from the analysis from this chart, we can say that bubble sort is much slower in terms of time complexity than the other two algorithms. And this is the bubble sort here. It's much slower because it takes a lot of time for it to load. In the table, it shows that quicksort consistently outperform the other algorithm, and this was to be expected in this case as the input data falls within a certain range. Now, quicksort perform better than the bubble sort and insertion sort. So that means it takes a minimum time for quicksort to run the random data, even in small data sets, medium data sets, and large data sets, and the data are random, they are not sorted. So quicksort perform better in this way. In the table, bubble sort, when the input size doubles from 5,000 to 10,000, the time for bubble sort does not double. It nearly triples from 88 meters seconds to 225 meters per second. Millisecond. This is the official proof of O-net square, which is the quadratic complexity, where the workload grows by the square of the input. From figure 1, insertion source actually drops after 5,000. This is an empirical anomaly. In real-world software architecture, JVM can cause fluctuation in timing that doesn't perfectly match theory. And from the chart, quicksort is faster because of its space complexity of linear in the worst case, whereas bubble and insertion sorts are also singleton. Now, this is the summary of what we're saying. The summary is that the bubble sort is time nearly triples when the inputs double from 5,000 to 10,000, and the insertion sort is what consistently outperform others most architecturally sound for random data. Quick sort, theoretically quadratic, but shows an empirical anomaly in this test. Okay, so rather this should be quick sort, and this is insertion sort. So here we see the bubble sum time nearly triples when inputs doubles from 5,000 to 10,000, and in quick sort we see that the consistently outperform others most architecturally sound for random data. And there's a big notation for bubble sort, for quick sort, or in insertion sort. The summary is the quadratic but shows an empirical anomaly in this test. So for sorted random data sets in which the data have been sorted, we have the input size of 1000 and the time is taken in milliseconds to perform these operations. And this is the chart for the sorted random data, and we can see that the insertion here performed well, then it follows the bubble sort, then the quick sort really didn't perform well. So let's see the analysis together. We see that in analysis, insertion sort and bubble sort become so optimized. They outperform quick sort because they only requires a linear walk, whereas quick sort still perform the logarithm partitioning, the recursiveness. In the chart, insertion sort is essentially flat on the x-axis. This proves that for a sorted data set scenario, which is the best case, is not architecturally efficient. It's most architecturally efficient. So that's to say that insertion sorts perform better because it takes, when a data is being sorted, insertion sorts work more efficiently best, and it shows that when the data is being sorted, quick sorts really didn't perform well here. Quick sorts become slow when the data is already sorted, as the algorithm does complex work that isn't needed. This means that more complex does not mean faster. And this is the summary of the sorted random data analysis, is that the insertion sort most architecturally efficient for pre-sorted data, and in bubble sort outperform quick sorts in this specific context, and quick sort here becomes slower due to unnecessary complex partitioning work. And we can see the time complexity here, the space complexity, and how stable they are, the average case, the worst case, and the best case for all this thing. And we can see that most of the time, like, the insertion are always stable, the bubble are always stable, and the insertion most of the time they are not always.